Welcome to Basic Skills Recap. Let's talk about domain. So we have these two kind of patterns where if you have a denominator in your function, you know that the denominator can't be 0 because dividing by 0 is undefined. And another pattern is if you've got a square root of literally anything, and we want a real valued output, what's underneath the square root can't be negative. Because if you take the square root of a negative number, that's not a real value. It's what's called a complex number. But if you don't know about those, we're going to talk about those later in the year. So let's apply these two basic patterns. What if we've got this, 5 minus 2x? So, in fact, let's make it even, let's do this one. So we've got this basic pattern. What I'm noticing is I've got a denominator. And what I know is that whatever value of x I plug in can't make the denominator 0. Because if it does, the result's undefined. So let's write what I just said. Denominator can't be 0. Algebraically, that's 5 minus 2x can't be 0. And so now you can solve for what value of x would make this 0. So I'm going to add 2x to both sides. And then I'll divide by 2 on both sides. So x not equal to 5 halves. And so that's the domain. It's okay to plug in any number for x as long as it's not 5 halves, because if you plug in 5 halves, that makes the denominator here 0. What about this? So you can do the exact same thing here. Here, if I've got something underneath the square root, what I know is that thing must be positive. So you can write it that way. It must be larger than or equal to 0. Same thing. Let's solve for what values of x make this condition that I know has to be the case actually true. So let's add 2x to both sides. Let's divide by 2 on both sides. So I've got that x has to be less than or equal to 5 halves. And if I plug in something, and so 5 halves is 2.5. So if I plug in something smaller than that, it has to be smaller than that. So let's plug in something larger than that. What if it's 3? If I plug in 3, I've got 5 minus 6, which gives me a negative value, and so the output would be undefined. So that's sort of basic. How would you find the domain for those kind of simple functions? All right, what about this one? So obviously there's a lot more going on here, but what we want to do is we want to notice the different pieces of this which fit these patterns. Because if you're going to plug in a value for x, and it's going to produce an undefined output, it's going to have to do it in one of these ways. So either a denominator is going to be 0, or something inside a square root is going to be negative. So you can figure out the domain of this by looking at the individual parts of it. So let's start both denominators. So what I know is this thing can't be equal to 0. So let's just zoom in on that part. I know that x times 1 minus x can't be 0. And so now you can solve for what values would make it 0. So obviously, if x was 0, that would be 0. So I know I can't plug in 0. I also can't plug in 1, because 1 minus 1 would make it 0. So coming out of this part so far, we have that x can't be 0 or 1, because that would make the entire function undefined. What else do we have? Let's look at this part of the denominator. So I know there's a square root here, but let's not pay attention to that part yet. Let's just focus on the fact that it's under the denominator, that it's part of a denominator. So here I've got root 5x can't be equal to 0, because if it were, I'd have 1 over 0, which would be undefined. So let's, again, solve for x. I'll square both sides. 5x not equal to 0. So obviously, x equals 0 is the only value that would make this true. So again, we know that x can't equal 0. So just for a different reason. So those are the same. All right, now let's focus on square roots. Let's start with this square root. So I know that 5x, because it's inside the square root, must be positive. So if 5x must be positive, it's also the case that x must be positive. So that gives me another condition. If I plug in x equals negative 1, I'd have the square root of negative 5, which wouldn't be defined. So I'm collecting a bunch of different things that have to be true here. And then at the end, I'm going to figure out how to put them all together. So let's keep going. So here I've got another square root. I know that 1 minus x must be positive. So if I add x to both sides, I know that x has to be less than or equal to 1. Okay, I think that's all of the places where I have square roots or denominators. So I've got all these conditions, and the last step is, let's figure out what they all mean when I put them together. So I'm going to imagine a number line here, and my question is, what input, like what values in the number line would be okay values for me to plug in? And these are the ones where it wouldn't be okay to plug in because it would produce an undefined value. So far we know that can't be 0, can't be 1. Here I've got that x has to be less than or equal to 1. So ordinarily we'd have, if it was this condition by itself, I'd have sort of a closed circle at 1 and any value less than 1 is okay. But we also know that it can't be equal to 1. So instead of a closed circle, it's going to be an open circle with this part shaded in. And anything larger than or equal to 1 is not okay. I know it can't be equal to 0, so I'd have an open circle right here at 0. I also know it has to be larger than or equal to 0. So larger than or equal to 0 would be like this. And so now my question is, what are the x values that don't violate any of these conditions? So it can't be 0, can't be 1. It can't be anything larger than 1 because this condition says it has to be smaller than 1. It can't be anything smaller than 0 because this condition says it has to be larger than 0. So the only values left that don't violate anything are values between 0 and 1, but not including 0 and 1. So we could say that the domain was x is between 0 and 1. Or if you want to use interval notation, you could say 0, 1 with parentheses, because parentheses correspond to open circles. So the endpoints are not included in the interval. Let's talk about transformations. So this is going to be a little more conceptual. Imagine that like what's inside this blob is some graph of a function. Obviously this is not a function because it fails the vertical line test because we have 2 output values for 1 input value. But instead imagine that you've got any function at all here, the graph of any function. Let's imagine what happens when we add 2 to the x value, we multiply the x value by 2, or we take the opposite of the x value. So each of these transformations is doing something to the x values before we apply the function. So all of these are horizontal transformations because they're changing x values. So adding 2 to the x value, you might expect would take it this way. It actually takes it the opposite way for a reason I'll suggest why in just a minute. A fuller explanation probably has to wait for another video. So this would be a shift left. Here, multiplying by 2, you might expect to stretch it, but again, it's having the opposite effect, so it's actually squishing it. So imagine taking all the x values and dividing them by 2. So your shape is going to squish and also get closer to the x-axis there. Sorry, the y-axis there. So this is a squish by 2. And here I'm taking all the x values and taking their opposite. So whatever the x values are, they are reflecting across the y-axis. So this is a reflection over y. But it's a horizontal reflection because the movement is horizontal. So what happens if I do those same things but on the outside of the function? As soon as you plug a value for x into the function and you get an output number, now we're talking about a y value. So this is like saying take your y value from your function and add 2. So that really is going to take all the y values and shift them up by 2. Here I'm saying take the y value and multiply them by 2. So that's going to stretch it vertically by 2. Here I'm saying take all the y values and make them opposite. So that's going to be a vertical reflection. So there you can see them all. Whatever the graph looked like, we're going to shift it up by 2 because we're adding 2 to the y values. Or we could vertically stretch it by 2. And you might wonder, how come we got some values that are more negative here? If you had any negative y values and you multiply them by 2, they're becoming more negative. So the stretch is away from the axis in both directions. And then for a vertical reflection, we'd take positive values and make them negative, or negative values and make them positive. So what should you take away from this? One big thing is remembering if you're doing something on the inside of your function, it's going to be a horizontal change. If you're doing something on the outside of your function, it's going to be a vertical change. I think that's kind of the biggest thing. So let's apply the ideas. What basic family is this? This is a transformation of 1 over x. But it looks like we've replaced x with x minus 2. So that would be inside the function. It looks like on the outside of the function, we're taking the opposite and adding. So these would be vertical changes. This is a shift up. This is a vertical reflection. And then here on the inside, this would be a horizontal shift, but not a shift left. Remember, a shift right. Oh, I forgot to tell you why that other thing makes sense. All right, well, hold on. I'll go back in a minute. Okay, so what does this shape look like? This is one of the basic families you should have memorized. You don't usually need to memorize a lot in math, but there's a couple of things that are handy to memorize. And then you got points at 1, 1, and -1, -1. All right, so what happens so let's apply these one at a time. What happens if I'm going to shift it right? So I'm just going to make like a little tiny sketch of it shifted right. So everything shifts, including these asymptotes. So the vertical asymptote at 0 is now going to end up at 2 because I've shifted it right by 2. And everything else kind of the same. All right, so that's after shifting it right. Let's go ahead and flip it vertically. So if I take this picture and flip it vertically, I've still got the asymptote at 2. Flipping vertically, what used to be in this kind of upper section is going to be in this lower section, and what used to be lower will become upper, like this. And then, I'm running out of space here, so then last step, so let's call this 1, 2, here's 3, this is going to be our final answer. We're going to shift it up. So here we've got a horizontal asymptote at 0, and we're going to shift it up by 3. So 1, 2, 3. And we still got this vertical asymptote at 0, and the rest of it kind of looks the same. So there we go. It's going to look something like this. Let's go ahead and fill in the last of the details. So here the vertical asymptote is at x equals 2. The horizontal asymptote is at x equals 3. What happened to these points? So the 1, 1 got shifted right by 2, so it became 3, 1. Then it got reflected over the x-axis, so it became 3, -1. And then we shifted it up by 3. So if it was at 3, -1, and I shift it up by 3, now it's at 3, 2. So again, you can think about the coordinates and how are they moving with each of your transformations. So let's try and apply an example the other way now. Let's say we have a graph and we want to figure out an equation which matches the graph. So in this particular case, I've drawn something like a cubic function, and I want to know what's a cubic that matches. So the first step is you have to have in your mind the shapes of all the basic families. So the cubic function ordinarily looks like this. So one thing I'm noticing is that this picture is actually reflected. And for a cubic, reflecting it over the y-axis is actually going to give you the same graph as if you reflect it over the x-axis. So you could reflect it either way. But in addition to reflecting it, it looks like we are translating it where this point at the origin is going to go over by 4 and down by 3. So let's do it step by step. So here I've got a basic cubic function. I could reflect it like this. So now this graph would look like the following. So now I've got kind of like the right orientation, but now I need to shift it. So I'm going to shift it right by 4. Because this is a horizontal transformation, I need to be modifying x. So I'm going to keep the negative sign in the cubed, but x is going to get replaced with x minus 4 because I want to change the x value before I send it through the cube function. So that'll shift it right by 4. And then last, I want to shift it down by 3 at the end. So that would be an example of applying the ideas of transformations to find an equation here. What about this one? So this looks like an upside down parabola. So I could start with x squared. And in fact, here I'm telling you to use a quadratic function. To flip it upside down, I would have a negative sign on the outside of the function. If you're curious what would it look like to do a negative sign on the inside of the function, it would be negative x squared, because here you see the negative is on the inside of what's getting squared. So this would be a horizontal reflection. But if you actually imagine horizontally reflecting a quadratic, it's going to reflect right onto itself, which isn't going to change it at all. And that's reflected in the fact that negative x squared is really the same as x squared. So the algebraic fact matches the geometric fact about the reflecting. Okay, if you weren't following that, that's okay. The important part is we want to be reflecting it vertically, so we put the negative sign on the outside. Now let's shift it. I want to shift it, let's see, left by 1 and up by 3. So left by 1 would be x plus 1. Up by 3, I'd add 3 on the outside. Okay, are we done? Well, let's plug in another point we know to check. So I know that 0, 0 should be on this curve. Oh, but you know, if I plug in 0 here, I'm getting 0 plus 1 squared is 1. So then negative 1 plus 3 is 2. So actually, this equation that I have is putting a point here at 0, 2. So what I actually have is a parabola that's more like this. So I need to scale my parabola. I need to stretch my parabola to make it taller so that the point at 0, 2 actually goes through 0, 0. Okay, well, a couple things I could do. One thing I could do is, let's imagine these parabolas are right side up. An unscaled parabola, if I go over by 1, it goes up by 1. So this is the graph of y equals x squared. For this one, it looks like if I go over by 1 from the vertex, I have to go this direction by 3. Because remember, this is at a y-coordinate of 3. So if I was going to plot this same parabola but right side up, it would look like this. I'd have to go over by 1 and up by 3. So what that's telling me is I need to stretch it by a factor of 3. So I would put a 3 on the outside. If you're lucky enough to have points that are close to each other and you can kind of think about it this way, that's great. What happens if you don't? If you don't, you can actually solve for the scale factor. And again, scaling just means stretching. It's like dilating. So let's put a number k on the outside here. And I don't know what k is, but I know that whatever number this k is, it's going to be a vertical dilation. So what I want to do is I want to plug in a point I know and then figure out what k value will make the curve go through that point that I know. So let's plug in the point at 0, 0, all right? So we'll have 0 for the y value, and then I've got negative k, and I'll have 0 for the x value. And now I can solve for k. Let's do it. I'll subtract 3 on both sides. And then this is just 1 squared, which is just 1. So what that tells me is that k must equal 3. And that's what I reasoned my way to over here by just thinking about kind of what does the stretch factor need to be. But you can also always just put a variable for whatever transformation you want, plug in a point you know, and solve for what that transformation has to be. So here at the end of the day, we've got negative 3, because the negative is coming from the reflection. So negative 3, x plus 1 squared plus 3. Let's look at composition. So what if I wanted to evaluate f of f of f of 2? Remember, the big idea of composition is the output of one function becomes the input for the next function. So a different way of visualizing this is, let's send 2 through the f function. That's right here. Whatever this outputs, that becomes the new input for another f function. Whatever that outputs becomes the new input for another f function, and then we finally get our answer out here the other end. So let's evaluate it one step at a time. If I plug in 2 to f, I've got 6 minus 4 is 2. So the output here is 2. So now you can imagine this input. I'm taking f of 2 again. So if I plug in 2 again, I've got 6 minus 4 is also 2. So this has become 2. And now I'm finding the last version, f of 2 is again 2. So if I was going to represent it this way, when I send 2 as the input to f, the output's 2. When I send it into f again, the output's 2. When I send it into f again, the output's 2. Okay, but what if f is a piecewise defined function? All right, so let's say f of x is defined by these three pieces. Remember that if you were going to try and evaluate the function, you're plugging in negative 1/2 for the x value, but how do you know which equation to plug into? That's what these intervals are for. You have to think, if x is negative 1/2, where is 1/2? Which interval is it in? So negative 1/2 isn't greater than 1. It's not between 0 and 1. It is less than 0. So that tells us that this is the right piece that we're going to plug into. So let's plug in negative 1/2 for our x. We've got negative 1/2. Okay, how are we going to simplify this one? At least one person in my class didn't remember what to do with this. The negative signs are going to cancel each other out, so we'll have 1 over 1/2. What if you don't remember how to do this? Very often, you can recalculate, or you can figure out this kind of stuff for yourself using just algebra, because this is what algebra is for. Let's pretend I don't know what 1 over 1/2 is. Let's give it a name. Let's give a name to my mystery number, because I know this is going to end up being some number, right? So let's call it m for mystery. So I know that 1 over 1/2 is m, and I want to know what is m. Well, I can solve for m the same way you'd solve for anything else. So what am I going to do? I'm going to multiply by the denominator here. So I've got 1 equals 1/2 m, right? Because I just multiplied by the denominator. If I want to isolate m, I know I could multiply by 2 on both sides. So now I've got m equals 2. Whoops. So that can always work for you. Now that you see the answer, you may have remembered at some point somebody probably told you sort of a rule where you like invert and multiply. So 1 divided by 1/2 is the same thing as 1 times what happens when you take the reciprocal here, 2 over 1, and that equals 2. But really the reason that rule works is because you're actually kind of solving this algebraic equation. So anyway, back to our original question. I'm plugging in negative 1/2. It's this domain, so I plug it in here. I get opposite of 1 over opposite 1/2. The opposites cancel each other out, and so now my final answer is 2. What if we were going to compose this? If I'm going to do f of negative 1/2, I'm going to approach it the same way. You can think about it as 1/2 gets sent to the f function. Whatever the output is gets sent through the f function again. So we just saw a second ago that f of negative 1/2, when you send it through f, the output is 2. So since this is really equal to 2, now we've got to figure out what's f of 2. And we'll do the whole thing over again, except with a different input, we're no longer using this piece anymore, because now f of 2, the x value is larger than 1. So now we're actually going to use this part of the equation to plug into. Because the big idea of piecewise functions is it's got a different equation for different intervals of input, for different parts of the domain. All right, so if I plug in 2 to this part, the output is root 2. So with an input of 1/2, the output eventually is root 2. What happens if I don't tell you an equation? What happens if we just got a big table of values? What would f of 0 be here? The important thing is to focus on the concepts, because in this class, we're very rarely going to show you the exact steps to take for whatever the problem is. Instead, you're going to have to understand what's the big idea, and then how does the big idea apply when I give you the information in different ways. So I might give it to you in a graph or a table or an equation, but it's the same big idea. Here the big idea is I take 0 as an input, send it through f. Whatever the output is, I'm going to send it through f again and see what my answer is. Only here we've got a table of values with a couple of inputs and a couple of outputs, but we can still apply this idea. What happens if I send 0 through f? Well, let's find out when x is 0, f of x is negative 1. So I didn't actually need to plug into an equation because it's already told me what the output is here in the table. And so then f of negative 1, let's find the x value for negative 1 is here. So then the output for f of x would be negative 3. So f of negative 1 outputs negative 3. So you can see, same idea. You just have to do a different set of steps based on your understanding of what the big idea is. Okay, what happens if you have a table of values and you're trying to figure out what type of growth does this represent? You remember from way back that the differences between the y values, well, so first you got to look at the x values, because growth is usually defined as how y changes when x changes by 1. So here x is changing by 1 every time. And here you can do some subtraction. This student looks like they didn't want to do that subtraction in their head, which is cool by me. So they started further down the table. And it looks like when you say like 7 to 0, so that's adding 7. Negative 26 to 7 is adding 19. So they're calculating these first order differences, and it's a bunch of different numbers. So then they're calculating the second order differences, and it's a bunch of numbers. So to get from here to here, I added 19. Here to here, I added 7. From 19 to 7, that's like subtracting 12. So they found the difference between all of these ones, and again, it's a bunch of different numbers. And those are the second order differences. If these had been constant, it would have been quadratic. But since it wasn't, they said, well, what are these third order differences? What do I have to do to get from negative 12 to negative 6? And the answer is add 6. And here we're seeing we're adding 6 every time. So it appears as if the third order differences are constant, and that's a cubic equation, which, just for reference, is an equation whose highest degree for x is cubed. So anything with an x cubed but no greater powers of x, that would be cubic. A couple of people in my block did this. All they did was look at what's the difference between these two numbers. So they said, all right, difference between 12 and 7 is 5. Difference between 7 and 4 is 3. So they were just looking at the absolute differences, and it didn't make any kind of pattern at all. But that's not the way. What you're really asking yourself is, what is the growth in y? So you're not looking at the difference between two numbers. You're saying, as x goes up by 1, what literally is happening to y? So here y is going down by 5. So it's got to be negative 5. And here it's going down by 3, so it's negative 3. Here it's going down by 1, so it's negative 1. And then here up by 1, so it's positive 1. And so now if we ask from negative 5 to negative 3, that really is going up by 2. Negative 3 to negative 1 is really going up by 2. Negative 1 to positive 1 is also going up by 2. So after we pay attention to the direction of the change, now we see constant second order growth, which is quadratic. So this would be an x squared type equation.